Hello physics students, welcome to your very first video in physics. And what we're going to do is, rather than start brand new stuff, we're going to revise the stuff that you should have learnt in physical science. But let's quickly just go through what we're going to do in physics. And we're going to do 4 broad areas. They're called Newtonian mechanics, electromagnetism, waves, atomic and modern physics. Now we won't cover everything that there is in the world of physics, unfortunately, because we only have a year and we are restricted a little bit with our time. So what we'll do is as much as we can. Now these are broken down into subtopics and you'll discover that as we go through the year. Now in Newtonian mechanics, the subtopics we're going to be looking at are motion, momentum and Newton's laws, work, energy, power, circular motion and gravitational fields. Now the first 3 of those are extensions to what you learnt in physical science, and so a lot of it's a little bit of revision. If you weren't great at them in physical science, you have an opportunity now to become great in them, and then we extend it a little bit. Excuse me. In the motion, for example, we go into slightly harder projectile motion questions. And the same with those as well. Our looking at forces and things is a bit more complicated. And the last 2 topics, circular motion and gravitational fields, is entirely new. So that's when we pretty much start the new stuff. So unfortunately we have to go through some stuff that some of you will either find quite easy because you got your head around it in physical science, or some of you will find it's a good opportunity to actually get better at it and to make sense of stuff that didn't quite make sense last year. So we're just going to quickly go through revision, and we're talking about motion in a straight line. We'll get on to curvy motion shortly, but we'll start off with just in a straight line. And excuse me again. We should remember there were a whole lot of terms that we used. And we had distance, displacement, vector scalar, speed and velocity and acceleration, and hopefully you've got an understanding of what they mean and what the difference of those are, and we'll quickly go through some of those as well. I forgot to push this little button here, which brings this little thing out here, and these are the equations that we're just going to start off using, and as you remember they are exactly the same as we had in physical science. So the first little recap we're going to do is the difference between distance and displacement. And distance is just the distance that, or how far you travel. And whereas displacement has a very precise meaning in physics, and that is the change in position of an object in a given direction. And so if we have something like a circle, okay, and if we have a start position there, and if you ran around the circle completely, let's say it was an oval, and you finished in your start position, that would mean that you had 0 displacement, even though you've run around the oval. So sometimes doesn't make sense. But a more complicated situation is if the finish is over this side. What's the difference between distance and displacement in those 2 cases? If we bring up our magic pen, let's see, and let's go for a color orange. Okay, so if I run, or you run around the oval here, let's see how calm I am. Oh, that's pretty good. Alright, and I finish there. That orange line there represents the distance I've travelled. Okay, and if I had a time for that, I could then work out the speed, because speed is distance over time. If, however, I wanted to work out my displacement, I would then draw a line from here to here, and that would be my displacement from my start position. Okay, and we should recognize that that would be 2r in this case, where r is the radius. And to work out my velocity, I would use this distance here. Recognize also that I really should have a direction, because displacement, direction, yep, So if I was to try and work out the displacement for this, let's go with a green. Okay, I'll put my north there, and I'd work out that angle there, because that would be the bearing, or I could work out that angle there, because that would be from south, whereas that's from north. There's a variety of ways of giving directions, and we'll quickly go through that shortly. Alright, let's move on. So, let's bring that up. And these were the formulas that you were introduced to in physical science. Nothing too much new there. Remember, there's no set equation for speed. We just sort of muck around with the one for velocity, but recognize that we're working out a speed, not a velocity. And the equation for velocity is just v equals s on t. Even though these triangles are there to confuse you, they just mean change in. So the change in your displacement and the time that it took. Couple quick examples. A trip meter on a car is set to 0, then you go on a journey, lasts for half an hour, and you travel 35 kilometers. What is the average speed? Well, speed is distance over time. 35 kilometers divided by 0.5 hours, and we get our answer in, because it's kilometers and hours, we get our answer is 70 kilometers per hour. Now we could have converted this to, just to remind you, we could have converted this to 35,000 meters, and then we could have converted this to seconds. The half an hour into, what's that? That's going to be 30 minutes times by 60, and then we could have worked it out, and our answer down below would have been meters per second. But we didn't need to, because kilometers an hour is a legitimate velocity, or common used velocity. If it had stated give the average speed in meters per second, you would have had to work it out. That's just the way it is. Alright, now let's go with a little more complicated one. In this case, a person rides a bicycle 5 kilometers east and then 5 kilometers north, takes 1.5 hours. Work out the distance, the average speed, the displacement, and the average velocity. So 4 questions from a very simple little task, and that's all the person did. They wrote along here and they wrote along here. Now notice these are our vectors which represent our displacements. Okay, and so we have an arrow on them and we join them head to tail. So we're sort of drawing a map. Okay, and we try and remember the difference between vector quantities and scalar quantities. Vector quantities will have a magnitude and a direction. So in terms of our distance, a distance is a scalar quantity, so we just want to know how far we've travelled, and so 5 plus 5 equals 10. And the average speed is going to be distance divided by time, which gives us 6.7 kilometers per hour. Now the displacement, however, we need to go from our start to our finish, which is represented by this arrow, and you must draw an arrow to represent a vector quantity, and that's our displacement. And we should recognize that to work that out we would use Pythagoras, and so S is displacement equals the square root of 5 squared plus 5 squared, which gives us 7 kilometers. Now because it is a displacement, we actually need a direction. Now we can work out the direction if we go, let's go with a blue, in that the direction that we move. Now, whoops, oh, don't be silly. The direction that we move, alright, there's our compass, that's north, that's south, and we're interested in that angle there. Okay, now we should recognize that that's going to be 45 degrees there, and that's going to be 45 degrees there. So no maths involved in this. So that angle's there is going to be 45, and if we click on it, where's my mouse? We get north 45 degrees east. So there's north. The 45 tells us how much to swing our arrow around. Now we could have swung it around this way as well, but that would be to the west, but we know it's to the east, so this one tells us which way to swing it around. Now to work out the velocity, we use our displacement and our time, and we get 4.7 kilometers per hour. but we needed that direction, and the direction is going to be the same as the displacement. Let's get rid of that writing. Here's some displacement and time measurements for a quarter horse. It's running around for 5 seconds and getting a displacement. We put in our data points, time on the horizontal axis as per usual, and we draw a line of best fit. We don't join the dots very rarely in physics. And we should remember that in this case the slope will give us the velocity. And to work out the slope, we do slope equals rise over run. We draw a triangle, a nice big triangle, as big as possible to make it more accurate, and we would get the speed in this case. Even though it's displacement, we're not given a direction, so in some ways we're also working out the velocity. But because we're not given a direction, we're not being as precise as we could be. Now some students understand this, but they hit a wall when they're given this, which is a negative slope. And so you just need, part of the problem is that they use this term rise, but there is no rise. And if we watch this little video next, I'll show you what we mean. Here's a positive slope, and this is our triangle we're using to work out the slope, and it's been measured quite accurately. It gives you the number, and there it is. There's our slope, rise over run. And if we play this little animation, we'll then make it a negative slope. So now it's a negative slope because the rise is actually a fall, and so you need to remember that that's going to be a negative number because that's a negative slope. And that sometimes confuses students because they just want to put in a number. They don't recognize that you actually have to change the sign of that number because it's a fall. Alrighty. And here's another displacement time graph, a little bit more complicated, but we recognize that the slopes here would give us the velocities. And there's our little triangles. In this case we'd use a nice big triangle there, and this negative slope here, what would we use? This triangle here or this triangle here? I would hope that you would use the larger triangle to work out your slope because it decreases the influence of the errors. The bigger the triangle, the less your error. And of course there's no velocity there. Now let's have another look at a question, another question. In this case it's a snail. Let's read this one, it's a little bit complicated. A snail starts at a position 20 centimeters from the origin and then moves to a new position 60 centimeters further away before going back past the origin to a position 20 centimeters on the other side of the origin. It finally ends up at the origin. Now that's a bit complicated, isn't it? So here's a ruler that represents the space that the snail's walking in. Not walking, sliming its way in. And if we we recognize that the snail doesn't actually start at the origin. Just because we say the origin is the origin, that doesn't mean that's the starting position. That's just our frame of reference. The snail actually starts here. Okay, it then moves 60 centimeters away. It then turns around, then moves past the origin 20, and then it comes, oops, I went a little bit too far. There's my eraser. Let's see if, oh, that does that. Silly me. It then, let's draw that again. Told you it was complicated. It then stops at the origin. Okay, so this blue line represents the total distance travelled, and the red line represents its displacement. Let's finish that. My writing's not fantastic this morning. Alrighty, so let's have a look at some of the questions they can ask us. Well, first of all, let's look at the motion graph. And so starting off at 20, now there's no time here, so they've made up the time. That's not important at this point in time. Get that? Starts off at 20, moves to 60, takes a while because snails don't move that fast. It then stops for a little while, again, takes a while to turn around, and then slimes its way back past the origin into negative space, stays there a little while whilst it turns around, and then comes back to the origin. So these are some of the questions they're going to ask for this type of question. What is the distance travelled by the snail's centre of mass on its trip? What is the final displacement of the snail's centre of mass relative to the starting point and the origin? Let's have a look at them. Let's get rid of those lines. And first of all, the distance. Now the distance travelled was the total distance, so it starts off at 20, goes to 60, so that's travelling 40, then goes from 60 to minus 20, so that's 80 centimetres is travelled, plus is 20, so 140 centimetres. You could work that out or convert that into metres, which is a good thing because that's a standard unit. Now what's its displacement from its starting position? So its final position was at the origin here. It started at 20, so 0 minus 20, it means its displacement is minus 20 centimetres because it's in the negative. If you remember, my little blue arrow I drew, was it blue or green? I can't remember. But it was pointing in the negative direction, wasn't it? And what's its displacement from the origin? Well, 0, because that's where it ended up. Now that's enough for this little video, and in the next video we'll continue on with our revision. Cheerio!